Next, let's define some terminology. Okay, we say G is a finite group if the set, G is also set, right? Set with operation with axioms is a group, so G can be also considered as a set if the set has set is a finite set. If the set G is finite, and the cardinality of that set is called the order of G. If you remember, the cardinality of a set means the number of elements of the set. Okay, but in the case of groups, we call it the order of the group. And if G is not a finite group, then we say it is an infinite set group. Let's see a few examples. The set of integers with addition is a set has has an infinite order. So that means this set has infinitely many elements. And similarly, the set of non-zero rational numbers with multiplication has an infinite order. And for a finite group, we can enumerate all the operations in the form of a table. For example, let's say we have a finite group with the order of n. Okay, then there are n elements. So we arrange these elements in this way. Then in this table, we write multiplication of these. So A1, 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 A2, A1, A3, and so on, and A1, AN. The order is important. A1 times AN may not be equal to AN times A1, so don't confuse the order. A2, A1, A2, 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 A3, and so on. So AN, A1, and AN, AN. Like this. So in this way, we can enumerate all the elements of the group and all the results of multiplications in this way. And this table is called the Cayley table of this group. Cayley is a mathematician, a name of a mathematician. Let's see a few examples. The first example is the group of only one element, and that element must be the identity element. And the Cayley table should be, so there's only one element, so E times E is E, right? So that's the only possibility. So this is the Cayley table. Okay. And a second example, let's consider a group of two elements. So the order of two. Let's say we have E and A, and we assume this E is the identity element of this group. So the Cayley table would be EA, EA. So E times E should be E, and E times A should be A, and A times E should be A, right? Because of the axioms of groups. So these are the only possibilities. But what about this one? So A times A can be either E, or A times A can be A. So which one is more plausible? So suppose we have A times A, that is A squared is equal to A. So let's take this one. So if that's the case, then if we multiply both sides uh, by the inverse of A, then this implies A is equal to E. But E and A should be distinct because we are assuming these are two different distinct elements. So this is a contradiction. So this cannot happen. Therefore, the only possibility is this. So we fill this blank by E. Next, consider a group of three elements. Let's say E and A and B. Okay, let's try to build the Cayley table. E, A, B, E, A, B. So E times E is E, E times A is A, E times B is B by the definition of the identity element. And A times E is A times B is B. So we have these four elements still blank. Now first consider A times B. A times B. This can be equal to either E or A or B, right? So these are the only possibilities. So suppose we have A, B is equal to A. Then this means by cancellation, we have multiplying A inverse from the left, we have B equals to equal is equal to E. But B and E should be distinct, so this is contradiction. So we reject this. And similarly, if we assume AB is equal to B, then it should be that multiplying B inverse from the right, we have A equal to E. So again, this is rejected because A and E must be distinct. Therefore, the only possibility is AB equal to E. So A, B equal to E. And by the similar argument, we can show that BA is also equal to A. So BA is equal to E. Oh, sorry. BA is equal to E. Now, we have A squared and B squared. So what are these? At this point, it is easy because for each, let's say, for each column, we have only one empty spot, and all the elements in one column must be distinct. So the only element that is missing is B. So this should be equal to B. And for B times B, it should be A. So why is it the case that all the elements must be distinct? So let's say in general, we have n elements again. So like A1 and AI and AI, AN. Okay. So for this column, we have A1 times AI, A2 times AI, and so on, AN times AI. So if two of them, some pair is are not distinct, then we have let's say if A1 and A1 AI is equal to A2 AI, then this implies A1 equal to A2, which is a contradiction. but this 1 and 2 can be any elements, right? So we could say, let's see, aj times ai equal to ak times ai. If this is the case, then by multiplying ai inverse from the right, we must have aj equal to ak. So two elements must be equal, but this is a contradiction. So that means every element in one column must be different from all other elements. And by the same similar argument, we can say if for each row, every element in a row must be different from every other elements. So far, in all these examples, we didn't specify what these elements are. These are just E is any identity element, and A and B are any elements. As long as they're different, it's okay. It can be anything. But here is one concrete example of a group of three elements. So the order three. Let's say we have the set of matrices, 3 by 3 matrices. So 1 0 0 0 1 0 0 0 1. So this is the identity element of 3 by 3 matrix. And 0 1 0 0 0 1 1 0 0. And the last element 0 0 1 1 0 0 0 1 0. Okay. So let's say we have this set of three matrices, three 3 by 3 matrices, and all of them are different from everything else, right? And consider the ordinary matrix multiplication between these. So if we set this as E and this as A and this as B, if you try to construct the Cayley table of this group, actually this is a group, you should check, and we have this table, okay, replacing E, A, B with these three matrices. Okay, so just multiply this and this, so that will correspond to this times this, so this should be equal to, right? So this is, by the way, this is just identity matrix, so it should be trivial. And if you multiply A and B in this order, you should get A and B in this order, so that the result should be the identity matrix, and so on. Next, we consider the group of order 4. So there are 4 distinct elements. Let's say E and A and B and C. And for this one, we need to distinguish two possibilities. So the first one is the case where there is an element in G which is not its own inverse. So its own inverse means so if an element is such that itself is its own inverse, then A squared is, for example, is equal to the identity element. But let's suppose A is not such element. So suppose A is not its own inverse. So we're assuming there is an element. So it means there is at least one element that is not its own inverse. So let's say that element is A. So suppose this one. And so that means either AB is equal to E or AC is equal to E, right? So either B or C should be the inverse of A. But without losing generality, we can assume this is the case. So forget about this one. If this is the case, then we just swap the labels of A, B, and C, and we can still assume this. Okay? So let's assume this. So at this point, the Cayley table would look like this. E, A, B, C. So the first row and first column, they're easy to fill. A, B, C, and AB is equal to E. AB is equal to E. So that means, but B is the inverse of A, so that means BA is also equal to E. So BA is also equal to E. And at this point, we can say that AC is not equal to C, or AC is not equal to A, because otherwise, uh, the first one, AC equal to A, implies A equal to E, and AC equal to A implies C equal to E, but these are contradictions. So that means we can assume AC is equal to B. There are no other possibilities. Of course, AC is not equal to E because A's inverse is B, right? So AC is equal to B. And from this, look at this column, this row. So we have A, E, B, and the only missing element must be C here, because the elements in a row must be distinct. And now look at this column. We have A, C, E, so the missing element is B. Now we have this block empty, and let's see. Now we have this. So let's multiply this by B from the left. So we have BAC equals to B squared, but BA is E. This part is E. So EC is equal to B squared, so B squared is equal to C. So B squared is equal to C, and the only remaining element in this row is A. And for this column, the remaining element is missing element is A, and for this row, the missing element is CBA, so that should be E. So this should be the Cayley table for this group of order 4. When we assume there is at least one element which is not its own inverse. Okay, so this is a big assumption here. In that case, we have this. And as a concrete example, you should check we have this group of 4 elements. This is a group of complex numbers. 1, I, negative 1, and negative I. Of course, I is the imaginary unit. That is square root of negative 1. Okay, for of course this is 1 is the identity element. Let's call it A, B, C, and we consider multiplication of complex numbers as the binary operator. Okay, then you should check this group with this binary operation satisfies this Cayley table. Now let's consider another case, which is actually the complement of the previous case. So the previous case was there is one element, at least one element in G which is not its own inverse. So if you take the logical negation of that statement, that becomes every element is its own inverse. Okay. Every element in G is its own inverse. Okay, so that means E squared is equal to E, but this is trivial. This actually is satisfied for any group. But not only that, we have A squared is equal to E, and B squared is equal to E, and C squared is equal to E. Because A is its own inverse, so A inverse is equal to A, right? And B inverse is equal to B, and C inverse is equal to C. So let's see. Up to this point, A, B, C, E, A, B, C. So the diagonal elements are all E. And of course, we can fill the first row and first column. Okay, now let's try to fill other places. Suppose, let's say, if AB is equal to E, then by multiplying A inverse from the left, we would have B is equal to A inverse, but A inverse is equal to A by assumption. So in this case, B must be equal to A, but that's not possible. A and B must be distinct, so this is not the case. And what about AB is equal to A? But that would imply, by canceling A, we have B equal to E. But that is again a contradiction. And AB equal to B. This would imply, by applying B inverse from the right, we have A equal to E. But again, this is not possible. Therefore, the only possibility is that AB is equal to C. So AB is equal to C. Then the remaining element in this row, the second row, must be B. Okay, and similarly, BA should be equal to C. Otherwise, there will be similar difficulties as these ones. So BA is equal to C, and for this row, the remaining element, the missing element is A. And for the second column, the missing element is AEC, so that should be B. And for the third column, the missing element should be BCE, that should be A. Yeah. So that's it. So that's the Cayley table for the group of order 4, given that every element is its own inverse. Okay, and there is a concrete example for this group, and that is the group of 2 by 2 matrices. 1, 0, 0, 1. So this is the identity matrix, and negative 1, 0, 0, negative 1. So that is negative of the identity matrix, and 0, 1, 1 0 and 0 negative 1 negative 1 0. So this set with usual matrix multiplication is a group with this type of Cayley table, and you should check. So multiply all these and find that the result is equal to this. Well, by the way, this group defined by this Cayley table is called the Klein 4 group. Okay, so any group of 4 elements, order 4, satisfying this Cayley table is called a Klein 4 group. And this is one realization of that.